Welcome back, guys. Today we're looking at 2.04, more rational functions. If you think back to the past couple lessons, all of these functions have been rational, right? They've all been fractions. So we're going to see that again, but we're learning something very new that's going to change the way you see domain and range. So of course, domain and range are part of our goals. Finding those for each type of function we see today. You should be able to also explain why asymptotes appear in graphs. We've already gone over this, so you should already know, but you should definitely know after today, because we're going to talk about that a little more. You should also be able to identify elements of a graph for irrational and reciprocal power functions. This is something, again, we've been doing over the past couple days. And finally, what's really new and kind of changing the way we see things today is finding holes in graphs. So what is a hole in a graph? What's it look like when it's graphed? How do we find it? That's what we're going to start with today with a question I have for you, which is, what do you think 0 over 0 equals? If you're thinking 0, think again, or better yet, think back to what I've said in the past. Anytime the denominator is 0, the fraction is undefined, even when the numerator is 0. Even then, okay? Make a note of this right now, because you need to know that when it comes to finding holes in graphs, you also need to know what a hole is and how to find it. Well, it's here written out for us in the yellow text. A hole is not an asymptote, but rather a specific point on the graphed line that is not a solution. So there's a specific point that's not a solution. That's new. That's a little weird, right? We're going to learn about that right now. And when does it happen? Well, it happens when you find a value. In other words, you plug an x value into your function everywhere you see x, and it gives you that fraction we just looked at, 0 over 0. If that happens, then you know there is a hole. Okay, so let's follow these helpful steps on the left-hand side as we go. First things first, set the denominator equal to 0 and solve for x. That's not too bad. Well, guess what you already found? That's the x value of the hole, if there is one. Now, I know there is going to be one, so I'll write it there for now, but we're going to discover it together, okay? The question now becomes, I know if I plug -2 into the denominator, I get a denominator of 0, but what happens when I plug -2 into the numerator? Do I also get 0? So let's try it. -2. Let's see, right here, I'll get +4. +4 minus 4, I do get 0 over 0. So that tells me there is a hole. Now, up until this point, you're used to plugging in x values into a function and you get out a y value. But notice what happened here. You get 0 over 0, which is not 0. It's undefined. So we can't say, great, the y value of the hole is 0 and we're done. No. If you do that, you're going to start to notice something weird. You're going to be thinking, every hole has a y value of 0? No, that's not the case. So what do? Let's go back to our steps. We substitute the value back in. We did result in a fraction of 0 over 0. And what's left is to simplify our function. And if you think back to semester 1, we did this quite a bit. How do you simplify this? Well, remember, we can't cancel out terms within a factor. right? Because right now, you could say that this entire numerator is a factor and this is a factor. Well, those aren't the same, right? And we can't cancel out 2's and 4's or anything else. We have to factor these further, if possible, to then cancel terms out and guide us to the end of our solution. If you look at this numerator, you should see a familiar polynomial that can be factored by a certain pattern being the difference of squares. So remember, the difference of squares pattern says if you have a perfect square minus another perfect square, you can factor them like this. But what is a and what is b? Well, a is the square root of the first term, which in this case is x, and b is the square root of the second term, which is 2. So we plug these values into our pattern here to give us x plus 2, x plus 2 times x minus 2. And if you're not sure if you did that correctly, you can always FOIL first, outside, inside, last, multiply those together, and see, do you get the polynomial you started with? If you do, you did it correctly. If you don't, you have to go back to the drawing board. Now, FOIL is not the only way you can check that. Remember, there's also the box method like this, where you put one polynomial on the top, the other on the side, multiply them out, and then combine like terms. We're not going to do that because you've done that quite a bit in the past, but we now have our factored numerator. So I'm going to get rid of this for now. If you need that, you can always rewind and pause. So I'm going to move this up here. And I'm going to rewrite my entire function with that factored numerator. Now, what about the denominator? Can I factor x plus 2 anymore? No, that is plain as can be. And lucky for us, that is the same as this factor in the numerator. So bingo, we accomplished exactly what we were hoping for to simplify our function. Now you actually just did two things. You created your new simplified function, which you can graph if you need to. We will in a moment. But you also have a function you can now plug the x value of your whole into to find the y value of the whole. Okay, so let's do it. We have -2, and that gives us -4, meaning when x is -2, y is -4, we have a whole at this point. And this is point slope form, or sorry, slope intercept form, right? Y equals mx plus b, right? We know f of x is the same as y. Mx plus b, sometimes it's plus, sometimes it's minus. But you should be familiar with slope intercept form. So we're going to graph this line with this whole right now. I'm showing you the original function, which we don't really need to mess with anymore. We have a nice simplified function, and we have our whole. Can you graph it? Me personally, I always like to start by graphing the whole because your graph line is not going to go through it, right? It's not a solution. So I find -2, -4, and I put my whole, which is an open circle or an open dot, however you like to say it. Now, this is slope-intercept form. Remember, I always say f of x is the same as y. So slope-intercept form, where this is the slope, this is the y-intercept. The easiest thing to graph first there is the y-intercept at -2. And what's the slope of this function? Well, you know that when you don't see a coefficient, basically what I like to say is an invisible coefficient is always 1. And we need slope to be in rise over run. So let's rewrite 1 as 1 over 1, which we can totally do. So now we have the rise over the run. So we're going to connect our dots with that slope. And there it is, our graphed function with the hole. Ready for another one? Let's do it. I know you are. We're going to practice with a different type of function, but not something you've never seen before. This is very simple. I think we can all see that now, but our numerator is not so simple. Okay, so I'm going to highlight that for now. We'll get back to it, but we're going to follow the same steps as we did before. First, checking, is there a hole? And if you want to test yourself, pause the recording. If you feel pretty confident, you can just follow along as we go. Okay, so we're trying to find out now, is the x value of 3 going to result in a fraction of 0 over 0? So we're going to plug 3 into our function. Everywhere we see x, we know the denominator clearly will be 0. But what about the numerator? We're going to get 9 plus 3, that's 12. 12 minus 12 is 0. There is a hole. Once again, okay, there is a hole, and we know, so I'm just going to write down here, hole at which point? Well, we know the x value is 3, y value is on its way. We need to now factor this numerator that I highlighted. How do you factor a quadratic with a leading coefficient of 1? Test yourself right now. Do you remember? We went over this in semester 1 quite a bit. There's also a handout in the recordings document that tells you how to factor a quadratic. Quadratic because the highest power of x is 2 and leading coefficient of 1. Invisible coefficients are always 1. So that's going to be factored using the x method. So we have a times c on top. Remember, this is in the form ax squared plus bx plus c. So coefficient of x squared is 1 times c, the constant, so negative 12. B goes on bottom, coefficient of x, which is an invisible 1. So we're looking for two values that will multiply to get negative 12, but also add to get positive 1. So we're going to look for factors of negative 12, but if they have to add to 1, to a positive number, what has to be bigger, the negative or the positive number? The positive number, right? So we know that we can multiply 4 times 3 and add 4 and negative 3, and that will satisfy everything in this x method. And this is just a quicker way than, kind of you could go, oh, negative 3 times 4, maybe 3 times negative 4, and you could just keep going and going. We thought this through, so we didn't have to do so much work there, okay? And these factors always have x times x, and you put in the values you found. So plus 4 and minus 3. This is our factored polynomial. Once again, you could check that by multiplying this together. Okay? So what happens? Well, we have our function with our factored numerator and our denominator, and lucky us, we have common factors again, meaning we have our new simple fraction or function right there. Okay, and the whole is going to have the x value of 3, and it looks like the y value of 7. Time to graph. Can you do it? I think you can. Okay, let's see how you did. 3, 7 is the whole. Again, slope of 1 over 1, but what's the y-intercept? It's right there at 4. 2 points is all you need to draw a line. So if you're not an expert at slope, as long as you have your y-intercept and your whole, you can connect those dots and you'll have your line. Beautiful. Believe it or not, this does get a little more complex in the sense that there can actually be more than 2 holes in a graph. Take a look at this function and try to answer this question. Why do you think there are 2 holes in this graph? And after you answer that, maybe try to answer what they are. So the reason there's 2 holes in this graph is because there are 2 factors with the variable x in them. If you look at your denominator specifically, you have a factor there and a factor here. 2 factors means you're going to have 2 x values that could make the denominator equal to 0, right? Okay, and we see that over here. Set this factor equal to 0. Well, that's just 0, right? So if x is 0, that will make the entire denominator 0. But also, let's see what we got here. If x is -1, that would make the entire denominator 0. Okay? And I'm not going to do all the work here. You could work it out and, here you already have some common factors. It looks like it's already factored out. And you could plug those in and you would find that those are both actually holes, okay? You have plenty of practice doing that, and this is already factored out, so we're not going to take up much time on that right now because there are other important things we need to look at, which are the vertical and horizontal asymptotes, okay? So we're going to touch base on that, and then we're going to focus a lot on domain and range. So again, vertical asymptotes, you should know those always start with x equals. These are vertical lines, dashed lines, perfectly up and down, right? And you know already that these are lines that a function approaches from the left or the right, but never touch. It gets super close, but never touches, okay? But guess what? Here's the kicker. Now there can actually be more than one vertical asymptote. That is possible. Okay, so write that down. But horizontal asymptotes, where it's y equals, meaning it is a flat horizontal line, there can only be one. But sometimes there's none. So those are your only 2 options. There's one or there's none. And here's some terminology in here that is new to you as well, okay? So if there's no horizontal asymptote, we say that that is top heavy, okay? Looks like I need a different color here. That is too dark. Let's try again. Okay, it's just not gonna show. That's okay. We call that top heavy if there's no horizontal asymptote. We call it bottom heavy if the horizontal asymptote is at y equals 0. Bottom heavy and positive or negative at the end if the horizontal asymptote at y equals that end value. Okay, I know that seems a little confusing, but we will see examples of it. And the same, it will be the same if the horizontal asymptote is at y equals the dividend of the coefficients. I know This part sounds a little confusing with no examples, but that's why we're going to look at some examples right now to make it make more sense. So when you're determining a horizontal asymptote, we talked about the four possibilities, right? They're right here. Top heavy, bottom heavy with a plus or minus, or the same, okay? So in this example, this is top heavy because the numerator has the largest degree, okay? You see x squared, this is x to the first. That means there is no horizontal asymptote, and we call that top heavy. If the denominator has the largest degree, and remember, it's degrees of variables, right? So we're only focused on the x here. Here, x is to the power of 1, and there's no x in the numerator, so clearly the variable with the higher power is in the denominator, so we call that bottom heavy, and that results in a horizontal asymptote at y equals 0. Okay, so what we're really talking about here is how to determine what and where the asymptotes are. If it's top heavy, there's none. If it's bottom heavy, it's at y equals 0. Okay? But there's two more options, right? If the denominator has the largest degree, which this does, you might think that's bottom heavy, and yes, it is. Okay, but we have this -1 being subtracted on the end. So if a number is being added or subtracted at the end, the horizontal asymptote is at y equals that number. So if that's -1, that horizontal asymptote is at y equals -1, similar to midline, if you think back to those sinusoidal functions. And finally, the numerator and denominator have the same degree. I should say if the numerator and denominator have the same degree, right? X to the first, x to the first, there is a horizontal asymptote at y equals the divided coefficients. So let's take a look. This means we call this the same, okay? Because the same power, right? X to the first, x to the first. The horizontal asymptote is at y equals 3 because of the coefficients of those x values, okay? Because right here we have 3. We know this is 1. 3 divided by 1 is 3. That's why we see it right there. Okay, review this. This is how you determine horizontal asymptotes, especially if there's more than one. So let's practice. That's right. It's time to practice. Let's see if it's sinking in. And if it's not, that's okay. We're just starting. You're just starting to learn about this, right? So what's the first step when finding vertical asymptotes? That's a great question in every math problem. What's the first step? Where do we start? We set the denominator equal to 0, right? That's what we need to do first. Now solve. Giving you time to do just that. And now that you've had some time, let's do it together. Set the denominator equal to 0 and solve for x. Oh man, that is a lot. What do I do with that? Well, it's not too bad. Remember, quadratics, leading coefficient of 1, x method, a times c, so 1 times -6, b is -1. Negative number needs to be bigger since it's adding to a negative, right? So what are factors of -6? That could also add to -1. So maybe -3 and 2. Let's see. -3 times 2 is -6. -3 plus 2 is -1. Beautiful. X minus 3 times x plus 2 equals 0. Okay. So what do we need to do? We're finding the vertical asymptotes, right? Meaning where x is equal to a value. So what we need to do is take each of these factors and separate them, setting them equal to 0 and solving for x. So take a look. Now we see that there is a vertical asymptote at x equals 3, but there's also one at x is negative 2. So these are both vertical asymptotes. So on your graph, you're going to see two vertical dashed lines, one at x is negative 2 and another at x is 3. Now let's do the same thing with the other one. Denominator equal to 0. Solve for x. Again, it's a quadratic. Again, x method. A times c. B. 5 on top, 4 on bottom. That's how I know it's going to be a 5 and a 1, right? Because somehow we'll subtract those to get negative 4. This would have to be a negative. So we factor it out. X minus 5 times x plus 1 equals 0. Separate. Solve. X is 5 and x is negative 1. Again, two vertical asymptotes. That's it for vertical. On to horizontal. What's the first step? Looking at your notes that you wrote down, right? I hope so, or took a screenshot. You need what you see in this peach box at the bottom. You need. Starting with asking the question, looking at your notes and ask yourself the question, is this function top heavy, bottom heavy? Bottom heavy with something being added or subtracted at the end, or is it the same? Well, here, clearly, this power is bigger than this power, right? So that's bottom heavy, meaning horizontal asymptote at y equals 0. And the other is also bottom heavy, but you're adding 1. So what does that mean? There's a horizontal asymptote at y equals whatever that end value is. So y equals 1. Okay? So notice, vertical asymptotes. There can be 2 for one function. Remember, for horizontal, there can be 1 or there can be none if it's top heavy. Those are your options. Not so bad when we worked it out, right? I think the terminology of this at first sounds a little more maybe intimidating than it actually is. We've made it to the point in time where we want to talk about domain and range, because think about it. Now we can have more than one vertical asymptote. Now there's holes in graphs, right? So obviously there's more restrictions happening, okay? So what does that mean for you? That means when you're finding the domain and range, you have to find the holes and the asymptotes first, right? Because the definition of domain and range, domain of a rational function is all real numbers except where there are holes or vertical asymptotes. And when it comes to range, so maybe I'll use some different colors here. That's domain. And when it comes to range of rational functions is all real numbers except where there are holes or horizontal asymptotes. So yes, This is becoming more involved. Don't stress it. Don't worry. Just take it one step, one problem at a time, and study and practice. That's how you get better. So let's go ahead right now and put it all together so we can properly write the domain and range. This is the last thing we're going to do, putting everything we've built up to together, okay? So we want to find the asymptotes, the domain, and the range. Step one, factor the numerator and denominator. Okay, this numerator, I see some common factors. I see they both share 2x. That's pretty obvious to me right away. If it's not obvious to you, you can write out all the factors. 2 times x times x. 4 is 2. Oh, let me erase 2 times x. See, they share things, right? They share a 2 and an x. So we have GCF of 2x. Factor that out. 2x times what would give us 2x squared? And 2x times what would give us negative 4x? So numerator is now factored out. Can you factor the denominator? Try. We have x cubed this time. So we can't just use the x method right away, can we? What we have to do instead is notice there's also a GCF of x, right? So what can we do? We can factor out the x. That gives us x squared plus 3x plus 2. Okay, but this is not fully factored, is it? We need to factor this quadratic now as well. So here we go. X method, a times c, b. The only two numbers that multiply to 2 and 1 that I know of are 2 and 1, and fortunately those add to 3. We still have the x on the outside. Can't forget about that guy. But now we have our x's, our parentheses, and plus 2 and plus 1. Now our numerator and denominator are fully factored. So I'm going to write out that function here. Numerator was 2x times x minus 2 over all of this. Oh, that should not be a parentheses, x plus 1. So what I did is I took my factor numerator and my factor denominator and I put it all together. Okay, now we can, just like before, cancel out common factors if they exist. Okay, I see a 2x and an x that could cancel out, but do we really need to do that yet? I'm gonna pump the brakes on that and go back to step 2 here, which is about identifying the wholes. Okay, because really what we needed is we needed this denominator factor to find the wholes because this is a bit of a mess, right? Now this becomes much easier to set each factor equal to 0 and solve for x, right? So I'm going to do that here. X equals 0, x plus 2 equals 0, and x plus 1 equals 0. Okay, I'm running out of space, so I'm just going to write it here. That's going to give us x is negative 2. And this will give us x is negative 1. So those are our possible, all three x values that will make our denominator equal to 0. But will they make the numerator equal to 0? Let's see. I'm trying to just jog my memory, see if there's a faster way to do this. Let's go back to the question. They want us to find asymptotes, domain, and range, but here they're also asking us to identify wholes. Okay. Identify wholes. Well, let's see. The numerator is not too complex, right? We could work that out. I'll just do that over here on the side. 2 times 0 times 0 minus 2. Well, 2 times 0 is 0, so that would make the numerator 0. So we know there is a hole with that x value. 2 times negative 2, and then in here we have negative 2 minus 2. Well, this, let's see, did I do that correctly? Negative 2, 2 times negative 2. Oh yeah, that would be, I don't think that's a hole. Let's see. Let's just double check everything here. So we have, here we got the x value of negative 2. If I plug that in here, I'd get 2 times negative 2. And that all times negative 2 minus 2. There it is. I made a slight mistake, I believe, because I had a feeling it was a hole. So I plug in negative 2's. This would give me, no, there's not a hole there, right? Because this would be negative 4 times negative 4. So no hole there. Let's check the last one. Negative 1, so 2 times negative 1, and then negative 1 minus 2. We're going to have negative 2 and times negative 3. That is not 0 either, okay? So we found a hole on our graph. And before we move on, I'm just going to confirm that. So just give me a moment to confirm. I want to make sure I'm guiding you in the right direction at all times. Okay, 2x squared. Okay. So x value of 0, that is a hole. X value of negative 2 is not a hole. That's correct. And then x value of negative 1 value of negative 1. That's a little harder to find. So that is also not a hole. Okay, so we did that correctly. Just wanted to be sure. Okay, so we identified one hole and vertical asymptotes. So remember how we found those before? We need to, just refreshing on this. Vertical asymptotes are basically those when you set the factors in the denominator equal to 0. So x equals 0 is a hole. So here's something to know. A hole can't also be an asymptote, right? They can't be the same thing. So this is a hole, but x plus 2, which is going to give us x equals negative 2, this is a vertical asymptote. And this we already solved as well over there. So x equals, so this is x is negative 2, and this one will give us x is negative 1. This is also a vertical asymptote. Okay, so we're going to put that all together. Well, actually, we have horizontal asymptotes now. This is quite the involved problem. So let's look at our original function. I would say it's bottom heavy because the highest power of x is cubed. So let's go back and look at our options. If it's bottom heavy, the horizontal asymptote is at y equals 0 unless something's being added or subtracted at the end, which it is not. Okay? Which it is not. So let's put it all together. We have a hole at x equals 0. We have our vertical asymptotes there. I think one of those values is off, right? Yeah, -2 and -1. And then horizontal asymptote at y equals 0. Can you list the domain and range? These could be quite involved. You need to take everything into account. Okay, let's do it. Okay, remember your domain and range for these rational functions always start and end with negative infinity and positive infinity, right? We went over that before. So we're going to start with this, but we have to piece together everything. So domain is possible x values. We're told x cannot equal 0, but we're also told there's a vertical asymptote at x equals -2. So you want to start by listing the smallest, we're going smallest to largest, right? Smallest x values that are not included. So -2, not included. Remember, that's how we show it's not included. United with, and then parentheses, again, to say -2 is not part of the solutions, right? What comes after -2? So let's kind of cross these out as we go. -2 is done. What's next? I see -1. -1 is also not included. What happens after -1? Well, we have that hole at 0, right? So we have 0 united with, and I thought this was far away enough, but apparently not. This is quite the domain, united with 0 to infinity. So with domain, we now listed all the restrictions on x. We had 3 of them, which is why you see 3 U's, 3 united, okay? Finally, range. What's not included? Y value of 0. Fortunately, that is it. So united with 0, going towards positive infinity forever. I know that last problem was a doozy, but practice, study this, and you will be fine. There's more practice as always. Make sure you use it, and I will see you guys next time.